Hi, everyone. This is Audio Engineering Society Germany Research Colloquium. I am Angelika, and today our guest is Michael Williams, who will tell us more about the 3D audio microphone arrays. If you would like to know more about upcoming events, you can subscribe to our newsletter. And to find more about what we do, check out our AES Germany website or the main AES website. Now, I would like to ask Ralph to introduce our guest.
Yes, thank you, Angelika. My name is Ralph Kessler, and I'm very happy to have a legend of the AES here, Michael Williams. Against his will, I'm presenting a little bit the character and the person and the scientist, Michael Williams. He started his professional career in the technical operations department at the BBC television studios in London already in the 1960s. In 1965, he moved to France to work for Société Audax in Paris, developing loudspeakers for professional sound and television broadcasting. He later worked for the Conservatoire National des Arts et des Métiers as a chief engineer in the adult educational television service. In 1980, he became a freelance instructor in audio engineering and sound recording practice, working for most of the major French national television and sound broadcasting companies, as well as many training schools and institutions. He's a member and fellow of the Audio Engineering Society, a former governor, and served the AES French section committee for over 2 decades, for instance, as a paper chair at international conventions. He has published many papers on stereo, multi-channel, and 3D microphone array recording systems for the AES and the Tonmeistertagung over the past 35 years. And I remember a paper in 1991, I think, Michael, it was the first one about 3D. So he really pioneered the topic. I personally have enjoyed all our past meetings and especially the sometimes controversial discussions at our joint conferences and conventions. I have always perceived him as a highly passionate recording artist and scientist who always confirms his hypothesis experimentally through his own large database of excellent on-site recordings. His lectures and books on multi-microphone array design are not only informative and full of knowledge and experience, but also enriched with a balanced critical mind and a good sense of humor. He has the rare gift of giving informative and entertaining lectures at the same time. We now look forward to such an experience and pass the microphone now to Mr. Michael Williams. Michael, the virtual stage is yours.
Thank you. Here we are. Let's start with some good old Decca bashing. What's wrong with Decca Tree anyway? Well, almost everything. If you want my opinion, essentially, the Decca Tree is just a set of pan-potted omnis. Now, let me just say that what I'm doing is starting with the Decca Tree to introduce it and see what I think is wrong, and then we'll go on to the Williams tree to give a bit more explanation about it. Okay, essentially, the Decca Tree is just a set of pan-potted omnis. Okay, the early days. The idea of the Decca Tree started in the early days of stereophonic recording in the late 1950. In other words, this is just about the time that I was going into the BBC in 1960. I can remember talking about this type of technique with my colleagues in the BBC at that time. And due to angular distortion, geometric distortion of the reproduced stereo recordings, people came to the conclusion that there seemed to be a hole in the center of the stereo sound image. I'm sure you've all heard of this kind of remark. Okay, now, this so-called hole, in fact, would have been better described as a spreading of the sound in the center of the reproduced sound image. That is what I call angular distortion. Now, if you take this XY microphone system, in other words, cardioid microphones, coincident cardioid microphones at 90 degrees, when they are produced, what happens is you get this crushing of the sound on either side. On each side where there's a loudspeaker, you get crushing towards the loudspeaker. And here's the problem: the spreading of the sound takes place in the middle. So this is where I get the idea that it's really spreading of the middle which creates this impression of a hole. It isn't a hole. There is sound here. And if you do special listening tests, you'll hear it. Whereas you do hear this crushing of sound towards the extremities of the main listening base at 60 degrees. Okay, so if we consider sound sources A, B, C, D, E, which are spread out evenly across the listening base, there's no angular distortion. If I now switch to a system with 5 degrees angular distortion, you can see that the sound sources B and D have been pushed towards the loudspeakers. They've been crushed towards the loudspeakers, and the middle has been spread out. So this is where this idea of angular distortion comes from. Now, I've tried to represent this angular distortion, this crushing, on the stereophonic recording angle diagrams that you probably all are familiar with. And you can see, for instance, here's the 5 degrees angular distortion. And on the other side, there's another symmetrical set of angular distortions at 5 degrees. If you go towards the level difference axis, in other words, the angle between the microphones, then the angular distortion increases from 6 to 7 degrees. And if you go down towards the time axis, in other words, the distance between the microphones, the amount of distortion, angular distortion, is increasing considerably. Now, I found that a lot of people, unfortunately, either didn't understand or were showing absolute no indication that they've understood what the consequences were of this angular distortion. So I decided to change the process of representing the angular distortion by putting 20 percentage values, for instance, 20%, 30%, 25%, 30%, 35%, right up to something like 45% of the maximum angular distortion that was possible when you get towards the level difference axis. And if you go down to the time axis, then you actually get up to values which are something like 60 degrees of angular distortion. When you have microphone systems which have omnidirection, for instance, or microphones that are parallel and have a certain distance between the capsules, then you can get up to something like 9 degrees of angular distortion, or something like 20% of angular distortion. Now, how do we get this value? If you look at the way systems developed at this time, you will recognize, I hope, the ORTF pair. You can see how they are presented on the stereophonic recording angle diagram. NOS is another reasonably well-known system. Then you have a few others, the Olsen, you have the Rye, and guess what? The German DIN system is slap in the middle of the minimum distortion value. So in fact, the best system here would be 90 degrees between the microphone and something like 20 degrees in distance. Okay, now, brilliant idea. Let's fill in the hole with another microphone in the middle. An acceptable patch whilst still in stereo. The middle microphone is pan-potted in equal proportions to the left and to the right. And these days, this seemed to be a satisfactory solution to the problem. This is something which I'm sure you all know about, but I just want to make it clear what direction we're following. Then came surround sound. This is really where the rot sets in. Well, that should get a laugh. The main problem at that time was that nobody seemed to have an idea of the function of the center microphone in the front triplet of a surround sound system. People were playing around with all kinds of things, systems, ideas to explain this problem and how to use it. And in fact, what I was hearing was absolutely nowhere near, I thought, was the actual reason for it. And then came along in 1991, a bloke called Mike Williams came along and published his first AES paper, 3157, on microphone arrays for natural multiphony. The term multiphony was later to become known as multi-channel or surround sound. I'm actually short-circuiting quite a lot of discussion which went on at the time, but through the years, this is the way my original choice of multiphony was to evolve to multi-channel and then to surround sound being an acceptable term. Looking back, I now realize that this was in fact the crucial point in time that defined the parting of the ways for me. I realized that I would be better following my own instincts and research results rather than trying to weave together the multitude of conflicting results of other people's work. And this has been something that has defined my work ever since. This was the beginning of what I considered to be a coherent approach to the analysis of microphone arrays for a surround sound recording, and later on the development of the 3D audio array and of course the Williams tree. One of my favorite proverbs is "He who travels fastest travels alone." This was said in 1917. I won't bother you with the second half of this proverb, but the original one was just "He who travels fastest travels alone." I did, however, have some much appreciated help along the way from Guillaume Ledoux, then a student at the Louis Lumière Cinema School near Paris. I therefore make no apology in pointing you almost exclusively towards publication of my own research work on the subject. I've recently published a new edition of my book on stereo, surround, and 3D audio, which is called Williams MMAD. And I've also created a new website at williamsmmad.com. And here's the front page of that site, which have a whole lot of interesting things that you can have a look at. Now, back to Decca Tree bashing. There are quite a few variants to the Decca Tree, but here is one that is frequently quoted: use of omnidirectional microphones. The base distance between the left microphone and the right microphone is about 2 meters, and there's a center microphone on the center channel at about 1.50 meters from the left-right base. In almost every respect, this is undoubtedly one of the worst possible configurations of microphones that could have been chosen, believe me. In fact, the use of 3 microphones for the front triplet of the array produces two distinct coverage segments, one to the left and one to the right. This should be pretty well known by around. This should be pretty well known by now. I've been flogging it for long enough. The specific coverage of each segment depends on the characteristics and configuration of the microphones, spacing of the omnis being the prime factor in this case. The wide spacing of 1.80 meters between the microphones means that that's between the left microphone and the center microphone, and between the center microphone and the right-hand microphone, means that the virtual sound coverage in each segment is very small, about 20 degrees. In addition, omnidirectional microphones produce the worst possible angular distortion of this small reproduced sound field. This is where we get down to something like 9 degrees or 60% of angular distortion. To all intents and purposes, and as I've said before, the system is just a very bad set of pan-potted omnis. Okay, let's have a look at this on a software that I've developed in the past for helping me to design surround sound arrays. It's software that I called CAMAD, Computer Assisted Microphone Array Design. This is its representation in of the Decca Tree. If you want more details about this, there's a paper that I presented in New York, in the New York Convention in 2011, paper 8461, where you can read all the details of the different possibilities. We've got this main screen here, which is showing the layout and coverage. And then we've got the screen that will present the array parameters, in other words, the distance between the microphone, the angle between the microphone, and a few other things that will take too long to explain now, but they do help with the control of the angle of the coverage segment. And on the other side, you have the distance, the coordinates of the microphones with 100 on one side, 100 on the other. And the front microphone is 150 centimeters in front. And here is the display of the array itself. You can see that we have the left and right microphone. We have the center microphone. There's 180 centimeters between the left and the center and the right microphones. And the important thing that you can read off this diagram is the coverage angle, which you can see is pretty small, round about 20 degrees on each side. 20 degrees on the left-hand side, 20 degrees on the right-hand side. This is where you will get the virtual image coverage on each side of the system. In other words, you see that there is a whole area. Let's go back. There we are. There's always this area here from the center to the left-hand side, to the right-hand side, and a little bit on the other side of the coverage area, which is just mono sound. There's nothing else. So in fact, all you're doing with a Decca Tree is taking this mono sound, pan-potting it into place, in other words, in the center, on the left-hand side, onto the left, and on the right. And then you're going to get this tiny little segment actually displayed as a proper stereo, if you like, image on each side. Now, let's have a change in philosophy. The Williams tree has been developed over a period of about 30 years. It's a carefully constructed range of microphone arrays covering each segment of the sound field and producing a smooth and accurate reproduction of the complete spatial sound image around us. The recording and the reproduction can be limited to only the upper hemisphere, or it can also cover the lower part of the sound image as well. Lower part of the sound image being the sound which is below the surround sound layer. So we've got a part which is covering the upper hemisphere, and we've got a part that is covering the lower hemisphere. In fact, the upper hemisphere is not just that part which needs one set of upper hemisphere microphones. We actually need a system which is a little bit more complex for the upper hemisphere. But here we go. Using the Williams tree, the quality of the complete 3D sound image is far superior to the Decca tree. And I hope it will become the standard approach to the recording and reproduction of 3D audio. I haven't done a lot of recording, which is comparing the systems, but you will see I've got one that I can let you listen to. Not here, but you will have the possibility to load it yourself. The recording and reproduction can be limited to only the upper hemisphere, or it can also cover the lower part of the sound image as well, that is below the surround sound layer of microphones. Williams tree can be divided into 4 component parts: the surround sound layer, the upper height layer, the lower height layer, and the zenith or top layer. Now, okay, let's go on from there. Each layer of the Williams tree has a number of different configurations. The surround layer can be any number of channels from 4 to 8, but more usually a quad layout, a multi-channel layout, in other words, 5 channels, or a Blu-ray 7-channel layout. It's rare to find other combinations which produce a 6-channel system or an 8-channel system, simply because there aren't any commercial systems available which can reproduce this type of thing. So 7, to my mind, is really tops. It produces a surround sound which is about the best that you can have, to my mind. The upper layers, upper height layer and lower height layer, are usually equal or less in number of channels compared with the surround layer. And of course, the zenith or top is a single microphone. But there is no restriction concerning the directivity of the microphones. You can choose anything from the range of first order directivities. I prefer myself hypocardioids or cardioids. Rarely do I find the use for supercardioids because there isn't enough bass in them, but cardioids or hypocardioids are my preferred choice. Let me just say a quick word about hypocardioids. I have this strange mental deformation where I do not talk about things called infracardioids or wide-angle cardioids. These are aberrations to my mind. I use the generic term, which is the hypocardioid, or if you want to go on the other side of a cardioid, it's a hypercardioid. So you have figure of 8 microphones. The next one along the scale is a hypercardioid or a supercardioid, almost the same. Then you have a cardioid. It's in the middle, a mixture of half omni and half bidirectional to get the final directivity. On the other side, you have the hypocardioids. In other words, there's more omni than there is cardioid. The result is a much better response in the bass. And I detest omnidirectional microphones. There's too much bass, even though the frequency response is quite linear, right down to very low bass. I find that it gives an exaggerated amount of bass. Some people, of course, like an exaggerated amount of bass, but I don't. Here we are with the CAMED software again. And this is where I'm afraid I have found no way whatsoever to present this on a screen that can be read on a smartphone. So you'll have to wait until afterwards and go into my website, for instance, to be able to look at this in more detail and use your zooming facility on a smartphone, your finger zooming facility, to be able to look at the different parts. Now, I'm sorry, but I've been working on this software for a very long time. It's getting between 10 and 15 years now. And there are still things that I've not been able to sort out, simply because I am not in any way an expert in MATLAB, and I've chosen to design this in MATLAB. So some things work, but I'm still trying to sort out some of the problems that I've got. Now, this is a 4-channel cardioid with cardioid microphones, 4 channels. And here you can see the coverage from this surround sound system, 90 degrees, obviously, it's a quad system. Now, if we then now go to hypocardioid microphones, I normally choose to have hypos with about a 10 dB attenuation at the back of the microphones. Still the same coverage, of course. The distance between the microphones has increased. So you're getting something like 33 centimeters between the microphones. Now, if I want to change the number of channels, I click on the channels. I've got 5-channel coverage, 5 channels, 5 microphones. These are cardioid microphones, and it gives you a coverage, distance between the microphones about 38 centimeters, 72 degrees between the microphones, obviously 360 divided by 5 channels. You can do the same type of design by using hypocardioids. Okay, so we've got hypocardioids for each of the microphones, same angle coverage, but the distance between the mics has now gone up to 47 centimeters. Now, if I want to go even higher, 47 centimeters, right, is beginning to be a bit of a monster. It's beginning to get bigger and bigger as we change the number of channels, increase the number of channels, and obviously go to hypocardioid microphones. And then we can change to 7 channels, cardioids, 7-channel cardioids. Therefore, we've got 51.4 degrees between the microphones and a distance of about, 67 centimeters. Okay, if we go to hypocardioids, still 7 channels, still 51.4 degrees between each of the channels. But you can see that we've now gone up to something like 75 centimeters between each set of microphones, 75 ECs, 75 here, 75 here, etc., etc., etc. Okay, so it's getting to be a big monster, but that's the way it is. You've got to accept that if you want to use time difference, and for me, it is absolutely essential that this is part of the component parts of design of these systems. If you're going to use time difference, then this means distance, therefore it means size. You're not going to make a small system with hypocardioid microphones. If you want to get to small, then you've got to go to a quad, and you've got to use cardioid microphones or even supercardioids if you want something down small. Therefore, sound recording all the way along the line is a compromise between conflicting factors. and size is conflicting with the type of microphone directivity and the number of channels that you're having. So you've got to work with all these things to find out what is the system which is really best corresponds with what you need. If you're going out recording outdoor sounds, there are cases when you need something small so you can get it up quickly, or you've got time to set it up. Normally for an orchestral concert, for instance, you will have more time to be able to set up these things. Therefore, you can afford to use more channels, 7 channels, and hypocordial microphones to get a much better bass response out of the microphones, but not as bad as omnidirectional. Okay, let's move on. We can now use any one of these surround sound arrays as a basis for recording the next 2 height layers, side and top. So we're going from surround into the domain of 3D. There are, of course, a few basic rules that must be adhered to if we're looking for critically linked, coherent, full 3D audio coverage. Critically linked, that's maybe a term we haven't come across yet. It means that the coverage segments are side by side, and we want a full 3D audio coverage from the system. The magic word being triangulation. This is a new term that I'm trying to introduce. Triangulation between each of the channels, 3 channels, obviously. We're talking about a triangle. This means that each microphone in an upper layer must form an acute scalene triangle with the adjacent pair of microphones in the lower array configuration. Sorry, I said that very badly. Must form an acute scalene triangle with the adjacent pair of microphones in the lower array configuration, and vice versa. Now, if you're having difficulty grasping that, I've done a very nice little diagram for you. Here's a 5-channel surround array plus a 5-channel upper height array plus a top microphone, and the 3D audio array showing the specific case of an isosceles scalene triangle highlighted in red for the side elevation segments and in yellow for the top zenith zone segments, in red for the triangulation of the side zone, and in yellow for the triangulation of the top zenith zone. So here we are, we have our red triangulation, whoops, and we have our top triangulation in yellow. Now, this means that we have about 6 3D audio arrays. If we just want to keep it down to this simple choice, 4 surrounds, 4 height and the top microphone, 5 surround, 5 height and a top microphone, or it's possible to have a 5 surround, a 4 height and a 1 top microphone, or 7, where's my arrow gone? There we are, 7 surround sound array, 7 upper segments, 1 height, or 7 surround with only 4 upper segments and 1 top microphone. Now let's go to the 4 to 4 start off with, and you hear a nice perspective diagram that I spent a lot of time trying to produce, and it's not looking too bad. It's not perfect, but it's not bad. So we have the surround sound bass array, right, left surround, right surround and left surround. Then we have the upper height array with the center, height back, height left and height right. And then here's the zenith microphone, the top microphone. Now, if you want to look at the triangulation of the upper layer and the surround layer, isn't this lovely? Okay, that's the side triangulation. And this side triangulation is the one that is going to reproduce the sound that produces the height perception in this first segment, this first surround segment. Then we can go into the top triangulation in yellow, and this is going to be the triangulation that will produce the localization over the top of the array. So you've got the side of the array being produced here and the top of the array being produced here. And this is the really important part of the design procedure. Here's a 5. Same thing. We've got a surround sound base, an upper 5-channel height array, and we've got the top or zenith microphone, as I prefer to call it. Here we are. Here's the triangulation of these two together. When you say that the middle microphone of the upper layer has to form a triangular structure in relation to the two lower microphones in this triangle. And then we have the same thing again for the upper segment. And we can now have a look at a 5 surround sound, a 4 upper layer, and the zenith microphone. And here we are, the triangulation between these 3 parts of the array. And let's go over to the 7-7. You're going to have to watch this because I think it's beautiful. So there you are. I spent a lot of time doing it. And here we go with the isosceles triangle for a 7-channel surround, and then with a 7-channel upper layer. And eventually we'll have the top triangulation with the upper layer and the zenith microphone. Now you can do this with 7 lower surround layers, 7 lower microphones forming the surround layer, the surround sound layer, and 5 microphones forming an upper layer and the top microphone. But you can see that triangulation is only possible here with this front set of microphones and the 2 above, or the set of microphones at the back, going all the way around at the back. And then if we put in the yellow upper triangulation between the zenith microphone and the upper layer, upper height layer, and then we can go to the extreme, 7 microphones making up the 7-channel surround layer, 4 microphones making up the upper layer with a zenith microphone. And you can see that here we're reducing the triangulation a little bit more. There's only 2 at the back here, which we're doing something. And here we're putting on the top triangulation, which produces localization over the top of the microphone system. Lots of lovely microphone arrays, I think you'll agree. So where's the problem? The problem is that each microphone array has to have its own specific univalent loudspeaker array to obtain optimum results. Univalent, this is something which people don't use very much. All it means is that we're building a system with one microphone and one loudspeaker linked together. And the question we have to ask ourselves, are we building microphone arrays for specific loudspeaker configurations? Or are we building loudspeaker configurations for specific microphone arrays? Sorry, my coffee was getting cold. Now, how would you feel to be a chicken? The only way to break this vicious circle is by magic. Well, what would you expect otherwise? I mean, of course, microphone arrays generating interformat compatibility. Now, this is a microphone array which generates interformat compatibility. In other words, if you want more details, then you'll have to go to my AES paper 7057, or of course you can read the section 14 or 614 of my book. We don't have enough time really to go into all the details. It's quite complicated setting this up. But we have 4 microphones in the middle. Now, if you take only these 4 microphones, you get a quad system. That's obvious. If you put one of the satellite microphones in, you have the quad plus 1 satellite. You have 5 microphones. You have a 5-channel system. And in fact, you have 5 segments. 1, 2, 3, 4, 5 segments. 1 and 2 are obtained with the combination of these 2. And the others are the simple 2 microphone setup on each part of the array. If you add in the LM, the left median and the right median microphone, then you have 1, 2, 3, 4, 5, 6, 7 segments. In other words, it's a Blu-ray system. If you put back in the last of the satellite microphones, then you've got an 8-channel system. So it means, in fact, with one microphone array system, you can record for practically any of the standard reproduction systems that we need. The big advantage of the Magic Surround, say, is that it is compatible with any of the standard surround sound formats simply by muting the unwanted channels. That means, folks, no remixing. You can throw your mixing desks in the bin. You don't need them anymore. It's a simple method to design a 3D audio array based on this Magic surround sound configuration. The height arrays can be 4 or 5 channel arrays, and the distance between the surround sound array and the height array depends on the side coverage that is required. I've found that a side coverage of about 35 degrees is probably the best for reproduction with the usual practical loudspeaker configurations, and certainly facilitates the critical linking of the top coverage segment. I, in fact, started off in the early days of experiment at Galaxy with work on a reproduction angle of 45 degrees. And as I started designing the whole of the system, in other words, getting critical linking with the top segments, this is where I found that 35 degrees was about the only solution that one could find which gave you a reasonable segment size here. I believe that Wilfred van Balen from Galaxy found the same thing when he was working on Aura 3D, that 35 degrees was a reasonable reproduction angle. And this depends also on the size, the height of the ceilings and the loudspeakers being placed up on there. Now, if you want to use a segment coverage of 35, it's no good. It's no good having the segment pointing towards the side, because we've already got microphones on the surround sound layer, which are going to cover the surround layer. So we've got to move these microphones so that we get a certain degree of steering. There's another term for it for you. We are able to move the segment coverage around by putting in a certain amount of steering. Now, if we use about 126 centimeters to get 35 degrees coverage, 30, 31, 32, 33, 34, 35 degrees of coverage, we can move the side coverage segment over, in this case, managed to move it over by 17.5 degrees. In other words, the segment coverage is moved over by 17.5 degrees, so that in fact, the bottom of this height coverage here is parallel with the surround sound coverage. Another way of doing the same thing is to use electronic time offset of about 1.04 milliseconds, in which case you leave the microphones where they are, you apply delay, electronic delay to the top microphone, and you shift the segment coverage over by about 17.5 degrees. Critical linking of the height array with the top or zenith zone segment is rather more complicated, I'm afraid, and is described in detail in my AES paper, the one I presented at Den Haag, and of course in my book. Here's the same thing, more or less, presented with a 5-channel surround array and a 5-channel height array. The difference is that the surround array is made with hypocardioid microphones, and the height array is made with cardioid microphones, and there is a 30-degree shift rotation of the upper array, so that we get this possibility to make good triangulation between the side microphones, and then later on with the top microphone. Here's a plan view. Wouldn't call it a plan view, sorry. This one is a plan view from the top, and this is a view from the side of the microphone array. And if you stick the whole thing together, then you've got a 5-channel. No, we haven't. We've got the side view of a hypocardioid surround sound array. We've got the side view of the cardioid array. And here's the actual segment coverage with the necessary segment steering, so that for the top microphones, these sides of the coverage are parallel. Now, let's have a look at this. This is a real situation, real microphone array set with surround sound microphone, upper layer height microphones, only 4 channels, because at that time I was doing testing with a 4-channel upper array, and we've got the Zenith microphone right up here, stuff that we're experimenting with, that we're doing at Galaxy at the time. And obviously, if we're going to do some microphone recording, we've got to microphone array reproduction. We've got to do some test signal recording. And this is what we did at the Galaxy main hall with the sound source. It's called a jam. Just a minute, I've got the system over here. I've forgotten the name of it. Yes, a Bluetooth Jam Street loudspeaker. And then here's the array, the surround sound array, the height array, and the Zenith microphone is up here. So with this system, I was able to track around the microphone system and also modify the sound source so that it could be, in fact, any position around the array. And then we could spend lots of beautiful hours listening to the same test track. Django Reinhardt was the one. And for days on end, we listened to Django Reinhardt. And you like it at the beginning, but at the end, you're pretty sick of it. Anyhow, here's one of the test loudspeaker setups that we did with 8 channels on the bottom, 4 channels in the height layer, and a Zenith microphone. And then we went on to more recent listening tests, which not very long ago, 2022. And here we have Raphael adjusting the Genelec 8341s on the straight up and the cantilever stands. And here you have a turnbuckle adjustment, which allows you to tilt the loudspeaker, these Genelec loudspeakers, so they are pointing exactly towards our listening point. This is where Lot came into operation. She was the expert for positioning the loudspeakers and for adjusting the time, in other words, the distance which the system was from the listener. And we did the actual positioning of angle and distance with a secretan theodolite with a laser beam mounted on the telescope part. And I had the very tiring job of supervising everything. And it did get a bit complicated, especially as the secretan theodolite was actually graduated in grades. In other words, 400 grades for full circle. And all my figures were in degrees, where only 360 degrees in a full circle. So it needed the agile brain of Lot to be able to transcribe these figures. Anyhow, the coffee in Galaxy, I recommend. It is some of the best I've tasted. Here's the main hall with the whole system set up with loudspeakers being placed in such that they're on isosceles triangles between their relative lower layer loudspeakers. There's one missing here, is the right-hand side of this system. We've got the right median loudspeaker. We've got the height right surround, but the surround right surround loudspeaker is missing. You will notice that we can look at the triangulation here, which is an isosceles triangle. But if we look at the height loudspeakers in relation to the lower ones, it's no longer a isosceles triangle. And I hadn't mentioned that before. this does not matter if the triangulation angles are within reason. They don't have to be isosceles triangles. They can be what's called acute angled scalene triangles. But this is the system that we've used for testing reproduction with the full setup and being able to switch between reproduction of the different systems according to which loudspeakers we switch on. And the result was completely satisfactory. On only one recording, unfortunately, only one recording was actually a reproduction of a complete 13-channel recording that I did here. The recording was in a church in Arbois in the Jura in France, and it was Pierre and Christian who gave me permission to publish this recording. Publish the recording so anybody can listen to the channels. You can take the full set of channels or partially a part of the channels. Now, if you want to do this, you've got to go to my website, go to audiophile downloads, and you'll come up with this link, which will take you into the full set of all the channels that you can download. You have the stereophonic quad, multi-channel, Blu-ray, or full 8-channel system. And here you have the channels that you can download according to which of these systems you want to listen to. You can add in the height. And here are the height channels, which you can add in the ones that you need to be able to produce the height effect, but it depends on which loudspeakers you're using. Not all of us, unfortunately, are able to have easy access to this kind of thing. And then you have the lower channels. If you have enough loudspeakers, then you can set yourself up with a full 19-channel reproduction system, and the sound is beautiful. The actual recording is a set of is taken from a concert recording of trumpet and organ. Here is a Scottish river, which they're soon going to use to make good Highland Scottish whiskey. Right.